So last time we were working on integrals involving powers of tangents and secant. And well, again, we discussed as well that the guidelines are not as clear as they are for sine and cosine. I mean, for when it comes to sines or cosines, you can never go wrong with those. Do you have an odd power of sine and cosine? Save one power of that function, multiply it with the dx, which is the part that will stand the du part of the problem when you write the rest of the powers in terms of the other function. If you have an even power of sine and cosine, just use the power reduction formula. So there's really no other tricks about sines and cosines. Well, in some cases, when it comes to integrating powers of tangents and secants, well, let's go back to the strategies here and recall that we have a couple of strategies when we have even powers of secant and odd powers of tangent. Well, so what do we have in this case for the next couple of exercises? Well, we have an odd power of tangent, but in this case, what do we have to do? So, number one, so I'm going to write this, in this case, yes, so for powers of tangents, we are supposed to save a factor of secant times tangent with accordance with the strategies here. However, we don't have any secants this time like we had over here, right? So we had an odd power of tangent, but we also had secants. We saved the power of secant and tangent. However, it's not the case, unfortunately, for this one. So what do we do? Well, so we need to go through other tricks, So in this case, well, since we are not going to have the secant tangent factor to turn everything into functions of secant, because secant's derivative is secant's tangent, well, a good way around to this is to write tangent cubed as tangent times tangent squared. And well, for tangent squared, we're going to use the identity secant squared x minus 1. And well, again, these are identities that we usually don't memorize, but yesterday, well, on Monday, I showed you a trick on how to derive those formulas when you don't have a formula sheet available, and those come from the usual Pythagorean identity sine squared plus cosine squared. And well, what are we going to do from here? Well, let's replace tangent x, and that's a secant squared minus 1, and have this into two integrals. And well, so in this case, we failed to obtain the secant tangent factor to multiply that with the dx. However, using this identity secant squared minus 1 to replace the tangent squared, well, in this case, we're going to do the other derivative, because secant squared, it's the derivative of what function? Anyone? Tangent. We have this tangent, we can set u equals tangent, and well, the integral of tangent, well, we have a couple of additional formulas here that we're going to use. Well, so if we set u equals to tangent du equals secant squared. So in this case, we can integrate u du minus the integral of tangent. I'm going to leave it like this for now. And well, so the integral will be u squared over 2 minus the integral of tangent, which is, or rather minus, ln of absolute value of secant plus c. And we'll just back substitute for u, which is tangent. And that's the integral. Okay. Let's look at the last question. You louder, please.
Yeah. So is this going to be on the test? I mean, this.
No, the exam is going to cover up to section. What chapter is this? Chapter 8 is or chapter 7? It's 7.2. This is 7. Oh, wait a minute. Oh, this is 7.2. No, so yes, this will be on the test. Yep. I thought it was no. 7.3 is what's next, actually. All right. Okay, so what about this last integral? Remember that exercise we did when we did integration by parts? The exercise e to the 2x sine x dx. Does anybody remember what did we do for that integral? It's one of those special integrals. Anyone? No? There was something very special about this integral, that we had to treat it in a different way as opposed to the other integrals. No? Yes. The u, well, u to the u equals to x. Well, so in this case, if we use u to the 2x, well, we have this sign, so the u substitution is not going to work. So no, this is an integration by parts formula, but it was one special integral that we had to treat it in a different way, not like the other ones. Exactly, we treat it like an equation. Remember that one? So the next integral, either integrals of, in this case, let me add a note here. Odd powers of secant and cosecant use integration by parts like an equation. That's what we did for that time. That's what we're going to do for this integral. Well, because again, we don't have a strategy for odd powers of secant in this case. Question?
Does this only go for the secant and cosecant?
Secant and cosecant. And you'll see you'll see it when we get to this. So, well, number one. Well, secant cubed, we cannot take u equals to secant because the derivative of secant is secant tangent, and unfortunately we don't have a tangent factor, so we can take advantage of it, so we can use it as a u du part, so it's not going to work. However, well, maybe if we split this into factors, if we separate into factors, say secant theta times secant squared theta d theta. Alright? And well, so in this case, essentially we have the product of the functions. And well, so when we have like the product of the functions, it might be the case that we have to use integration by parts, and this will be the case now. Recall from integration by part the acronym LIATE. Well, unfortunately, it's not going to work because what do we have here? What kind of function is this? Trigonometric. And what kind of function is this? Also trigonometric. So there will be no way to classify the hierarchy of the function, so we can set our u very easily. However, if you observe the two factors, which one is easiest to integrate? Secant squared, because secant squared is the derivative of which function? Tangent. So that's going to be our, also in this case, u equals to secant theta, and dv will be the secant squared. theta d theta. So the derivative of secant du will be secant tangent, and the integral of secant squared, that's tangent. Alright, so we have the four parts that we need for our integration by parts, and let me write down the formula. So the integral of u dv equals u times v minus the integral of v du. Well, that's going to be u times v. In other words, oh, again, I'm going to write the original problem every time, because we're treating this one as an equation. So u times v, that is secant times tangent, minus the integral of v, which is tangent, times secant tangent, which is the du part. Okay? Well, number one, let's simplify this. Tangent times tangent will become, okay, secant theta tangent theta minus the integral of tangent squared secant theta d theta. All right, and let's observe this integral right here. Well, this is still equal to the original problem. Okay, so tangent squared. So the derivative, if we set u to be actually the tangent, well, the derivative of tangent would be secant squared. However, we only have one power of secant, so we're in trouble. We cannot use the u substitution method unless we had power of 2 over here, but we don't have that power of 2. Okay, so let's see. How about writing it, okay, using the previous step? Well, secant tangent is the derivative of what function again? Well, we don't have a secant here, so we can set it as our u. So we're in trouble here. So how about we use trigonometric identities once again, and we're going to use for tangent squared secant squared minus 1. So that's the integral of secant cubed that's secant tangent minus the integral of secant squared theta minus 1 secant d theta. Well, this will be further split into two more integrals. So that's going to be negative secant squared times secant. That's the integral of secant cubed. Do you notice where are we going to? We're getting back to the original problem. And minus minus becomes a plus, the integral of secant theta d theta. Oops, secant tangent. All right, so it's the integral secant cubed. Okay, so number one, we have the same integral as the original problem, so that's why we treat this like an equation. And let's instead add the integral of secant squared, secant cubed theta d theta plus secant integral of secant cubed theta d theta secant tangent, oops, no, not here, not here. And well, what's going to happen here? Number one, these two are going to get canceled, and one integral plus another integral, how many integrals? Two integrals. And that's a secant tangent. And okay, what's the integral of secant? Well, that's one formula that we have at the top of the page. The integral of secant is the natural log of the absolute value of secant plus tangent. And at this point, that's plus ln of secant plus tangent plus c. And all we do is divide both sides by 2 to leave the integral alone. Okay? Integral of secant cubed theta d theta secant secant tangent plus 1/2 plus 1/2 ln of secant plus tangent plus c. And in this case we don't write c over 2 or 1/2 c because this is just an arbitrary constant, and a constant divided by 2 is just another constant. Alright, and that's final answer. And again, that's how we treat in a very specific way these powers of odd powers of secant and cosecant. In this case, integration by parts. All right. And well, so let's see. All right, so for this section 7.3, we're going to evaluate integrals that contain radicals mostly, that otherwise we couldn't evaluate using the techniques we learned in Calculus 1. And also, we couldn't evaluate this as well using the method of integration by parts or any other weird substitution. So, well, just so you can see, so we can relate with something we did in Calc 1. Well, actually, there's a little typo here. That's supposed to be the integral from 0 to positive 1. Okay, so no negative here. It's actually positive 1. So let's consider this problem: the integral of the square root of 1 minus x squared. Well, so let's consider the function that we are integrating. So this is some function y that I'm going to write over here. Y equals the square root of 1 minus x squared. And if we solve, or rather if we get rid of the radicals, square both sides to get y squared equals 1 minus x squared, and have all the variables on the left, all the numbers on the side. That's x squared plus y squared equals to 1. Okay, what is this equation describing? It's a circle, right? Okay, so we have a circle. Also, we are evaluating this integral. What kind of information is the integral giving us in general? The area under the curve in general, but in particular the area under the circle. But do we want the area below inside of the entire circle? Not the entire circle, because again, if you go back and solve for y over here, you're going to get y squared equals 1 minus x squared, and y should be plus or minus the square root of 1 minus x squared. In other words, you would get two solutions to the equation. The positive solution would represent the upper semicircle, while the negative solution would represent the lower semicircle. And in this case, well, coming back to the integral right here, which part of the circle are we integrating over? Is it the upper semicircle or the lower semicircle? The upper, and we can tell that by the sign. Unless we had a negative, well, that'll be the lower. And then, well, so let's draw a picture here. So we have half of the circle, negative 1 to 1, and we want to find this area right here. Right? So Well, even though we cannot integrate this function, and the reason why we can't integrate this function is because if we set u equals 1 minus 2x, du would be negative 2x. I'm okay with the negative 2. We can fix that. However, we're missing one factor of x, so we can use that the u part. So unfortunately, we cannot do that. However, in Calc 1, you evaluated this integral using geometry. And this is what we're going to do. Number one, the area of the circle, which is pi r squared. However, we are not finding the area of the entire circle. We're finding the area of only 1/2, all right? Because that's only the upper semicircle, not the lower semicircle. So all we have to do is 1/2 pi. What's the radius of the circle? What was that? 1. It's a 1, right? So that's 1 squared, and this is pi over 2. All right? Okay, so that's what you did in Calculus 1 when evaluating a definite integral, but in this case using geometry, not in an analytic way, because we didn't have the tools to evaluate these integrals back in Calculus 1. Now, in this class, in this section in particular, we're going to learn how to compute an integral like this, with, well, maybe in some cases with limits of integration. We're going to learn the method of trigonometric substitution. And well, what do we need for the method of integration by trigonometric substitution? Number one, we would have to know pretty much every single trigonometric identity, because we're going to use them a lot. All right, not just these ones, of course, the basic ones, you know, like the reciprocal ones. I didn't list them here because I think at this point in Calculus 2, those basic identities are basically a second nature, you know. However, the ones right here, the Pythagorean identities, this one, we use it all the time. These two, on the other hand, tangent squared plus 1 equals secant squared, and cotangent squared plus 1 equals cosecant squared. Well, again, you're not required to memorize them, but on Monday I showed you a trick to obtain those two identities. Other identities that we need are the double angle formulas for from trigonometry as well, for sine 2 theta, and keep in mind that cosine 2 theta has 1, 2, and 3 different versions, as opposed to the sine 2 theta. Nevertheless, the one that we're going to use the most, just to give you the heads up, is the one for sine 2 theta. We're going to go back to the half angle or power reduction formulas, the same formulas that we did in the previous section. Well, you know them already. Just so you can see the difference here, recall that the sine squared has a minus and the cosine squared has a plus in between. That's one way to memorize them, using some kind of a pattern recognition. And other integration formulas that we also need to know, it's the integral of secant, the integral of cosecant. Well, we already used this one in the previous section on the last example. And mostly you need to understand how the Pythagorean theorem works. I mean, I think it's like one of the simplest formulas in the world. C squared equals a squared plus b squared. I mean, a quantity squared equals to the sum of the squares of two quantities. What could be hard about it? Well, so we need to have a good understanding of how this formula relates to the sides. Well, number one, there is another version, if you will. There's another version of this formula in which if we solve, let's say, for a squared or b squared, that's going to be c squared minus a squared. But what we need to understand here is when we use this formula, this version, that's going to give us c equals to the square root of a squared plus b squared, all right? But well, I mean, yes, we're only taking the square root, but how is this meaningful to the method? Number one, going with the picture of a right triangle. What would this A represent on the right triangle when using the Pythagorean theorem? What about B? Another side, okay? I know it's like a very simple idea, but actually it's crucial when it comes to do the so side and side. Now be careful here. What if you use the other version of the formula? That is, instead b squared equals c squared minus a squared. What does the c represent in the Pythagorean theorem? The hypotenuse and one of the sides. So the hypotenuse and side. And notice the order of the difference matter, just so we can make a numerical sense of it. Because, well, on a right triangle, which side is the longest of them? Well, it makes sense to subtract a shorter number from a larger number, so that we get a positive number, because if we do the subtraction in the other order, then we're in trouble, because we would be getting a negative number inside of the radical. And does that make sense to work with imaginary numbers? No, at least not in this class. All right. And well, the reason why I'm stressing on having an understanding of how the Pythagorean theorem really works, it's because I'm going to take a different approach than the book takes. Well, essentially, and this is the part I disagree with the book. The book asks you to memorize a table with 3 different substitutions. You mess up a sign, you're screwed. The whole problem is wrong. And well, so memorizing a lot of information, there's always a lot of room for this kind of silly mistakes. However, understanding on another topic, it's the way the book does it is by doing the substitution and then doing like 6 or 7 steps just to simplify this radical part. The way I'm going to show you the substitution, it's going to take, we're going to get rid of those 6 or 7 steps, and we're going to write everything into essentially 1 or 2 steps, and it's going to go really, really quick. Of course, you're free to go to the textbook and read it so you can compare. We are going to obtain the same results, but you will find out that the way the book does it just takes forever. And doing this same substitution, simplification of the radical, 5 to 7 steps, it's just repetitive and annoying. So, number one, how are we going to evaluate one integral like this? Number one, it's important to write the integral as, well, the integral of something squared minus something squared. So in other words, what quantity squared equals to 1? What quantity squared equals x squared? X, all right? Well, so what do we have over here? Number one, we need to make a distinction of what do we have. Do we have a difference of squares, or do we have a sum of squares inside of the radical? It's a difference of squares. Okay, let's go back to the Pythagorean theorem. If we had a sum of squares, those quantities would represent the lengths of the sides. However, because we have a difference of squares, the first quantity will represent the length of the hypotenuse, and the term with the negative sign would represent one of the sides. Which side? I'm going to tell you which one in a second. Well, this means hypotenuse and side. Okay, so we're gonna set a triangle, a right triangle, with this angle right here to be the reference angle. All right, so let's label out the sides of the triangle. And well, the hypotenuse is the number whose square is 1. That's going to be 1. And x will be one of the sides. Now, which side? Preferably the side that is opposite to the angle. In this case, it would be this side. Okay? Now, let's find the length of the missing side. So the length of the missing side, we do it by using the Pythagorean theorem. But I mean, if you do 1 squared equals x squared plus whatever quantity squared, you should get back to the same radical over here. 1 minus x squared. Right? Okay. Now from here, we need to set up 3 parts in the substitution. Number 1, we need to relate a quotient that involves the radical function. Okay, actually there's a couple of possibilities. Okay, don't write this down yet. The number 1 possibility is to write radical 1 minus x squared over 1. And now here is where SOHCAHTOA comes into play here. So which trigonometric identity would be this one? Cosine, because this is adjacent over hypotenuse. All right. The other possibility to obtain a quotient that involves square root of 1 minus x squared is to divide it by x. All right. However, in this case, well, let me raise the trig function. Between this quotient and that quotient, which of the two is simpler than the other one? The first one or the second one? The first one. So go with the simpler one. Go with the first one. And well, this will be cosine theta, which is the same as saying, well, I'm going to reduce this 1 minus x squared equals to cosine theta. Now, we need a second substitution. We need a quotient that relates the quantity x. And there's a couple of possibilities. Number 1, x over 1 or x over square root of 1 minus x squared. Which of these two is simpler than the other one? The first one or the second one? Okay, get rid of the second one. Now, x over 1, what trigonometric function is this one? Sine. Sine theta. Okay, and this reduces to x equals sine theta. Okay? Now, from this expression, the one that relates to the x, we're going to use this to obtain the dx. Dx equals what's the derivative of sine, which is cosine theta d theta. Okay, so we have everything that we need to do the substitution. So that's number 1, that's number 2, and that's number 3. In some cases, we may not need all the 3 elements, but in some cases, well, in this particular case, we don't need the x element because we don't have a sole power of x. Now, let's back to the integral, and well, we did a substitution for the radical. Isn't that equal to cosine theta? And dx becomes cosine theta d theta. Okay, so that's the trigonometric substitution. Let's evaluate the integral. And trust me guys, with this, I've just saved you around 10 minutes of work. By doing all these couple of quotients, I saved you 6 or 7 steps, which take a good minute and also are repetitive, using the same trigonometric identity all the time. So let's see, cosine times cosine, isn't that cosine squared theta? And well, we evaluated integrals like this one in the previous section. In this case, we have an even power of cosine. We will have to use one of the identities. Let me go back to the identity sheet. In this case, the power reduction formula, in particular, 1 plus cosine 2 theta over 2. So let's see. That's the integral of 1/2 1 plus cosine 2 theta d theta, and that's 1/2 the integral of 1 d theta plus 1/2 the integral of cosine 2 theta d theta. Okay, well, let's integrate these two terms. The integral of the theta equals 1/2 theta plus 1/2 the integral of cosine, which is sine 2 theta, times another half, the 1/2 that comes from doing the baby u substitution on this one. And this plus c. Let's reduce. Plus 1/4 sine 2 theta plus c. Now, we just finished solving the problem in the world of theta. So what we're doing is we're given a problem that we cannot solve in the world of x. We need to send this problem to another world that in which we can easily solve this problem. Well, we already did solve the problem. We already got the solution. Now we need to go to take this back to the original world, which in this case it's the world of x. Okay, so but number one, there's a couple of issues here. Notice this last trigonometric function here, which is a sine 2 theta. The setup that we did for the right triangle doesn't call for 2 thetas. It actually calls for a single theta. So that's where we need the trigonometric identities. We need to further simplify these ones. And let me go back. We will require, like I mentioned before, this is the one that we're going to use the most. Sine 2 theta equals 2 times sine theta cosine theta. Okay? So this is equal to 1/2 theta plus 1/4 2 sine theta cosine theta plus c. And I think we're almost ready to get this. Oh, let's simplify this first. 1/2 theta plus 2/4, that's another 1/2 sine theta cosine theta plus c. Well, we can write sine based on the information that we have from the triangle, and using SOHCAHTOA, sine equals to opposite, which is x, over hypotenuse, which is 1. And for cosine, using SOHCAHTOA, this is adjacent over hypotenuse, which is 1. However, we have an issue with this angle. We need to do something about that theta, because yes, we will be able to write this sine and cosine in terms of its corresponding expressions of x. However, what do we do with the sine? Well, in this case, check this out. Use this as your starting point. Use the sine x equals to sine theta, and well, isn't this the same as saying, whoops, isn't it this, you know, theta equals arcsine x, or inverse sine of x by inverse properties, inverse functions properties? Well, so number one, we will replace this theta with arcsine x plus 1/2 sine, again opposite over hypotenuse, that's x over 1, and cosine radical over 1, that's adjacent over hypotenuse. Plus c. And well, let's just clean up the parentheses here. So this will be 1/2 arcsine x plus 1/2 x square root of my 1 minus x squared plus c. Okay? Yes, even though the integration in the trigonometry world took a good minute to go, trust me, I still saved you like 6 or 7 steps that you don't want to be annoyed of. All right. Okay, so for the next example, well, I really don't want to rush through because no, I'm not gonna make it in 4 minutes. So